Thank you very much for the invitation and also for the kind introduction. So I'm sorry that I cannot join you in person, but I'm glad to be able to participate virtually. So this talk will be about building quantum machines. And this, which is a part of what many of us view as a quest for controlling quantum world. So in this quest, what we're trying to do is we're trying to isolate and control simple quantum objects and then build more and more complex systems. And what we hope to do with the systems is to explore new physics with these engineered many-body systems, like create and probe new states of matter, but also to explore new applications in areas such as quantum information processing. So as this audience no doubt knows, this field is very active. It's a lot in the news, but it's actually important to remember that this field faces two big challenges. One of these challenges is we do not know if and how we can build truly large-scale quantum machines, systems having millions of good qubits. And moreover, even if we can build them, to be honest, right now, we do not really know what can they be good for. I mean, there are some ideas, there are some potentially high-impact applications, but there are very few of them. So, part of the work that I'm going to tell you about today is aimed to address these two key questions. You can also look at this field as a kind of an ultimate quantum rivalry, and this can be understood in many different ways. It can be a competition between different platforms, sometimes between different countries. But in some way, one can, like from the Eastern perspective, philosophical perspective, it's actually much more fundamental. It's a competition between two forces of nature. One is a force of controllability, where you would like to keep quantum systems isolated and fully controllable. And another one is scalability. You would like to have, many of them. And these forces are at work, these contradictory forces are at work in many different parts of societies. For example, you have an organization which has a lot of PhD physicists. By definition, such an organization is very hard to control. But this is definitely a big challenge in the field of quantum information. And specifically, the current frontier of the field involves tasks, executing tasks that modern classical computers cannot do, and it involves systems beyond 100 physical qubits. And using this kind of machines, what we hope to do is we hope to build bigger and better quantum machines and also start addressing this application challenge. So I call this time an era of quantum discovery. So, and I hope I will illustrate it with a couple of examples. So specifically what I would like to do today is tell you about how we built in our lab quantum machines atom by atom, assembling large arrays of isolated neutral atoms and how we make them talk to each other to execute, for example, quantum logic operations. And then I will tell you about some recent experiments using this machine involving exploring two-dimensional quantum phases and two-dimensional systems, probing topological order and applying them to try to accelerate combinatorial optimization. Then as an outlook, I'll talk about most recent work involving developing a new architecture for quantum processing, which is based on reconfigurable atom arrays. So in our lab, we build quantum systems literally from individual atoms. We do it by starting with the gas of pre-cooled atoms, pre-cooled using conventional laser cooling techniques for atoms in a vacuum chamber in a gaseous phase. And then we shine into this vacuum chamber the tightly focused beams of light. So these beams of light attract the atoms to the point of the highest maximum. And so these focused beams of light act as optical tweezers. We focus these beams very tightly, such that each individual tweezer can contain at most one atom. So two atoms do not fit into this tweezer and get ejected. And so what we do is we don't start with just one tweezer at a time. We start with thousands of tweezers and try to load them all together And on each given shot, we end up with a configuration where some traps are full and some are empty. And in order to get rid of this entropy of this disorder, what we do, we literally take a picture of atoms, figure out which of these traps are full and which are empty, and then basically eliminate the empty trap and then reconfigure the rest of the atoms in a desired array. With that, we end up with atoms which are separated by a couple of micrometers typically. So at this point, they do not talk to each other, they do not interact. To make them interact, we excite them in a state with quantum, high quantum, principal quantum numbers, so-called Rydberg states. And that's the way how we can execute logic gate, how we make the atoms interact. So this effort is by now several years old. It's a collaboration, joint project with Marcus Greiner, my colleague at Harvard, and Vladan Vuletic, our colleague at MIT. So let me talk a little bit more about this Rydberg excitation because it's a key ingredient of the scheme. So we like Rydberg states because they have a combination of long lifetime and very strong interaction. So in fact, if you excite the atom into the state with n equals 100, the van der Waal interaction between the Rydberg atoms in the states is 14 orders of magnitude stronger than the van der Waal interaction in the ground state atoms. So 14 orders of magnitude is a big number, and we can make a good use of that. So the specific way how we like to utilize this Rydberg interaction is based on something which is called Rydberg blockade. So what is it? So if you take the atoms and start trying to excite them resonantly, if the atoms are far away, then these atoms will just undergo independent Rabi oscillations. But if you bring the atoms close together, then eventually this Rydberg interaction will take over, and the doubly excited states will be shifted and will be shifted far away from resonance. So what it means, if the atoms are brought close to each other, then you will be able to excite one atom or another, but never both at the same time. So that's the essence of the Rydberg blockade. And basically it means that simultaneous excitation of atoms is blocked at distances smaller than this blockade radius. And we like it to use this technique to entangle atoms because it's very robust. Once under Rydberg blockade, entanglement of atoms isn't sensitive to motion or to position of the atoms. To summarize, the way how we will, do quantum computation and quantum simulations is we will start with the disordered array and then, sort the atoms to prepare the desired initial state, and then subject these arrays of atoms to multiple laser pulses, changing the internal states. And then at the end, we will do projective readout, just read out the internal state of the atom. So we can use this approach in many modalities for many purposes, such as quantum computation, for example. But one specific application, which I think is gives a very nice illustration, is the idea of programmable quantum simulators. So basically, that's the idea, literally implementing Richard Feynman vision, 40-year-old vision, when he first envisioned how quantum computers can be built. So to illustrate it, let's consider a one-dimensional spin chain of equally spaced atoms. And let's try to just excite them homogeneously to the Rydberg state. So at this point, these atoms can be thought as two-state objects, where two states are ground state and Rydberg state. And the evolution will be given by this Hamiltonian, where the first term is a spin flip, the second term is laser detuning, it acts like as a chemical potential, and the third term describes the interaction. So to understand what kind of many body states we can simulate, we can create, let's consider a ground state phase diagram of this Hamiltonian. You can parameterize it with two parameters. One is this laser detuning or chemical potential, and another one is interaction range. So if the interactions between atoms are completely negligible, then this laser detuning, determines the state, the many body state. So specifically, if the laser detuning is negative, then it's energetically favorable to have 0 atoms in a Rydberg state at each location. So n is the number of Rydberg atoms on each side. So that means all atoms should be in a ground state. If the tuning is positive, then all atoms should be in an excited state. But clearly a state like this is not consistent with Rydberg blockade. So if, for example, only nearest neighbors are blockaded, then the most Rydberg atom you will be able to excite is half with this configuration up, down, up, down, up, down. So the state like this, breaks Z2 symmetry. So this is like an anti-ferromagnetic state, we call it sometimes Z2 ordered. But if you now start extending the range of the blockade, you will also create a state where not just nearest neighbor, but second nearest neighbor is blockaded, and this kind of logic can be continued. So what you see now is that basically depending on a blockade range, depending on the interaction range, you should be able to enter states with different symmetry broken. And the way how we can explore it is actually very simple. We can just start with all atoms in the ground state, adjust blockade radius, and then just try to enter all of the states. This is one of our earliest results, where on a slower panel, we just use only nearest neighbor blockade. So we create a state, basically up, down, up, down, up, down, anti-ferromagnetic state. In the middle row, so we change, in this case, atom position to make sure that not only nearest neighbor, but second nearest neighbor is blockaded. So then the state we create is up, down, down, up, down, down. And then here is the state with Z3 symmetry broken. So basically, what you see in this simple example is that by programming the interaction, we can enter different phases with different symmetry broken. Actually, these phrases, turns out to have very different properties. They have, for example, different phase transitions, but this example really illustrates the use of this machine as a programmable quantum simulators. So since this early work, which by now is 5 years old, this field, I would say, really flourished. So there are now many different atom and molecule arrays that are being explored in laboratory around the work. And actually, we'll hear about some of this work from Junhee, from Professor Choi, newly minted Professor Choi, later in this talk. And basically, this platform is now actively used for various type of experiments, from many-body quantum dynamics to quantum computing, quantum metrology, and all of these directions are actually very closely connected. In our lab, since about 2.5 years, we are now operating what we call a generation 2 atom array. So this system is powered by the device called special light modulator. It's basically a computer-generated hologram where if you reflect light from this device, you can basically shape the image that it produces. So basically, here are some examples. And by just creating appropriate hologram, you can create, in this case, a 2-dimensional array of traps, of optical beams. So if you project it into the vacuum, so you end up with this 2D trap array. In this case, it's more than 1,000 traps. The downside of this special light modulator, which is actually a remarkable device, is that it's slow. So to basically move atoms, to sort atoms in this array, what we'll use another a second set of tweezers, which is created by 2 acousto-optic deflectors, which are basically which are positioned 90 degrees with respect to each other. One of these, so acousto-optic deflector is basically a device which is similar to that used for bar scanners in supermarkets. So it's a device where you can feed in some radio frequency tones and it deflects a right beam in a certain way. So basically, we use these 2 acousto-optic deflectors to sort rows and columns of the atoms. And it's all computer controlled. And there is another thing which I should note. So this upgrade was completed, about 2 years ago, a little bit, like 2.5 years ago. And then we know remember what happened at the time. So this actually this last day when we were allowed in our labs before we had to shut down everything, but we were allowed to operate servers in the during the shutdown period. So we had a week of warning, and during this week, this experiment became a server. In fact, everything what I will show from now on are the data which has taken, which have been taken remotely. So these are the kinds of artificial atomic crystals we can create. These are just various arrays which we can create using the system. We can also create an arbitrary atomic pattern. So here is one example that is a desired pattern. So you press a button and here is an atomic image. And so basically in this second generation, we start with about 600 traps. And as a result, we create about 300 sorted atoms. Each trap is filled with probability more than 99%. So how can we use this system? So the easiest thing is we could just try to basically explore quantum phase transition in two-dimensional arrays. So let's consider first a square lattice. There were atom positions like it's shown here, and we adjust blockade radius such that we only block the nearest neighbors. And then if we do the adiabatic sweep, then sometimes we see these images shown on the right. So it's basically completely ordered antiferromagnetic pattern. Admittedly, this is not what comes out on every shot of the experiment. So to analyze what comes out, we have to look at correlation function. So for example, here is a density-density correlation function, which shows that you have this antiferromagnetic correlation spread across the entire array. And one can also analyze these images microscopically. So for example, it turns out that these states, perfectly ordered states, do not occur very often, but they are still the most probable states that are created. So it's actually, this state and the state complementary to it. And when one can also ask what's the probability to create the ordered state, and this probability actually decreases with system size. But this decay corresponds to basically a 3% error in quotes, which is accumulated during the entire evolution. This error includes everything, includes imperfect evolution, imperfect preparation, includes also quantum fluctuations in the final state. So, but at the end of the day, so this initial atom state and the final atom state are completely classical. So how do we know if we have quantum dynamics, if quantum fluctuations play any role? So in order to do that, what we can do is we can try to study the nature of this phase transition. And in fact, this transition should be an Ising quantum phase transition in 2+1 dimensions. It has been studied theoretically for many years extensively, but it has never been observed experimentally. To observe and study it experimentally, what we do is we basically go across this phase transition with different speed. And we use the idea of quantum Kibble-Zurich mechanism, which connects dynamics across this transition to universal scaling exponents. So, and these observations are actually quite dramatic. So if you go slowly across the phase transition, then correlations spread across the entire array. But if you go quickly, correlations stop growing very quickly. And so we can use these images to study, for example, like how correlation length grows. And then we can use the ideas of the universality of quantum phase transition. So basically, the phase transitions in some sense are expected to be universal, governed by just two numbers, two so-called critical exponents. So this universality appears if you rescale all of these curves with the speed with which you go across a phase transition. And basically, if you rescale it properly, all of these curves should collapse. And indeed, they actually do. They collapse on each other. And by optimizing this collapse, you actually can extract, for example, this correlation length critical exponent, which actually turns out to be very close to what is predicted theoretically for quantum phase transition in 2+1 dimension. So, and these exponents, for example, are different for boundary transitions or for classical transitions in open systems. So that's how we can actually benchmark the quantum many-body dynamics, but it's also really kind of a unique tool to explore the nature of this phase transition. In fact, in this case, observe the phase transition in 2+1 dimension. So using all of these tools over the last 2 years, we had actually a lot of fun. So it's a very special time in this field and in our lab in particular. So what we have done is we explored various kind of complicated phase diagrams in two-dimensional systems. We studied non-equilibrium quantum dynamics and in fact made a small discovery. So we discovered a phenomenon which is now called quantum many-body scars. We probed topological phases, and I will talk a little bit about that in the following. So we also use this platform to accelerate combinatorial optimization and also make some steps to scaling up the system and developing universal programmable quantum computers. So I'll talk about all of these things in the following few minutes. So I should also say that in addition to our university machine, there is now a second machine in town across the Charles River. We have a startup company, Quera Computing, which actually has its own instrument very similar to what I've shown, and this instrument will actually will be publicly available later this year through the AWS Bracket service. Okay, so in what follows, I'll try to give some examples of recent work in this field, and in particular, I will first focus on these ideas of topological spin liquid. So, topological spin liquid is a kind of long-standing, long-elusive goal in the field of condensed matter physics. So this actually is a form of matter which was literally postulated by P.W. Anderson. And the idea is that this is a form of matter which should appear in the so-called frustrated systems which cannot easily order. And in these cases, under some conditions, you should actually be able to create a phase of matter which have properties which are determined by systems topology. So this phase should have quite exotic properties. For example, it should be robust against perturbation. It should have long-range quantum entanglement, should have some emergent gauge theory, and have exotic excitations like an anionic excitation. And this search for these kind of states have been a major effort in condensed matter physics for the past several decades. About 20 years ago, this field, got a different, injection of energy and momentum through the work of Alexei Kitaev, who pointed out that such states can be used for robust quantum information encoding and processing. The famous example, the so-called toric code. So despite all of these efforts, there has been no conclusive experimental evidence of this kind of phenomena in any system today. About 2 years ago, we were very excited where there were two theoretical proposals by our theory colleagues, by Subir Sajdev group at Harvard, and in particular, a proposal by Ruben Varsin in Ashwin Vishwanath's group, who showed that this kind of phenomena, topological states of matter, can be created and probed in the Rydberg arrays. The idea is the following. So you start with this lattice where atoms live on the links of the Kagame lattice, and this is sometimes also called the Ruby lattice. And you adjust the blockade radius such that each block or atom blocks 6 of its nearest neighbors, like shown here. And so under these conditions, it turns out that you can actually map this model into the model of the so-called dimers. So basically, to each Rydberg atom, you can put in correspondence a dimer which lives on this link. And the idea of these dimers is that, these dimers cannot touch each other. So none of the vertices in this lattice can be touched by more than one dimer. And so this model is, of course, frustrated. There might be a lot of these different dimer coverings. And actually, what Ruben and Ashwin showed is that, in a case like this, you should have, we should be able to create the states, which is basically a coherent superposition of all of these dimer coverings. So this is the state which should have the so-called Z2 topological order. It's also very closely related, it's basically identical to something which is called resonating valence bond. All right, so how can we create and probe such state in our experiments? So we can create a lattice of this type and then try to adiabatically evolve our system into this dimer state. And what you see here is just one of many snapshots which we obtained. So this kind of looks like a dimer state, but at least approximately, but it's really very hard to see if there is any order here. So in fact, in each given experimental run, you will get a different state which looks differently. So how can we detect and study topological order? So the idea is that we need to study some kind of topological observables, in particular, these so-called topological string operators. So, and these are very similar to the stabilizers of toric code. So basically product of sigma x and sigma z's in toric code, which in a closed loops. And the way how they appear in our model can be nicely illustrated, looking at diagonal z strings. So if you have a perfect dimer covering, if you make a loop which goes around one vertex, so then this loop should cross one Rydberg excitation or one dimer. And so if you associate +1 to the atom in the ground state and -1 to the atom in the Rydberg excitation, then the product of these sigma z operators here clearly will be number 1 and -1. And if you now make a bigger loop, which goes around several vertices, so then the expectation value should be -1 to a number of enclosed vertices. So this, corresponds to basically a kind of a parity of dimers along the strings in a way that actually is like a Gauss law to the underlying gauge theory. So this is the kind of stuff that we can measure. So specifically what we can do is we can make a kind of adiabatic transition into the state and stop at various detunings. And what you see here is that close to a quarter filling, there is a kind of a change in the slope of this line. And at this point, this product of the Z strings really acquires, some non-zero expectation value, which actually has a right parity depending on how many vertices you include. So clearly, the signal decays if you increase the size of the loop. However, we can see some non-zero signal even for the loops which are, fraction like half of the size of the array. So these string operators reveal transition into a dimer phase. However, at this point, it's not really clear if this state which we observed is really a coherent superposition of these dimer coverings, or it could be just a statistical mixture. So this observation do not tell us what we are seeing. So in order to really distinguish that, we need to study off-diagonal string operator. So the string operator can be defined as follows. So when you apply it to the side of triangle, it basically flips a dimer across this triangle using this loop. So this is not kind of quite non-trivial. So, but why is it actually even a good observable? Well, if you make this string closed, it turns out that this type of transformation takes one dimer covering and maps it into another dimer covering. So in a way, this closed string acts very much as a sigma x operator for a normal qubit. And we know that if you want to show that, we have coherence between state 0 and 1 for a single qubit, we just need to measure non-zero expectation value. So it turns out we can measure this, this string. So the way how we do it is we basically map this Z string, X string into a Z string by using this collective rotation, by just, pulsing the light onto these atoms, under certain conditions. And to make a long story short, so we can measure this expectation value of this product of this kind of X operators, and we see across a very large domain of parameters, we see non-zero expectation value, which shows that we have a coherence between dimer colors. So with all of these tools, how can we say that we're entering the topological phase? So in order to do that, we really need to reveal the topological properties, and it can be done by comparing closed loops to open strings. And the result of this measurement is quite dramatic. So if you basically look at closed loops, then at some point we have a non-zero signal emerge. But if in the same state you estimate the open strings of similar length, you see the signal is dead zero here. Likewise, if you look for X strings, there is a parameter domain where this X loops have non-zero signal, but for closed loops, and the open strings are exactly zero. And actually, you can make these considerations more formal by defining an order parameter, which actually is a ratio of open string signal to the closed loop signal. And basically, when both of these order parameters are zero, vanish, while the closed loops have some non-zero value, this kind of uniquely distinguishes this quantum spin liquid from other phases. And indeed, what we find is that there is a parameter domain where this conditions hold. So that really means that we are kind of observing an onset of topological spin liquid. So at this point, we became very tempted to try to create a kind of a first, small topological qubit. So here is our attempt. So in order to do it, we create a system with non-trivial topology. We just make a little hole, so which actually kind of equivalent to this idea of making like a hole in a donut. So it makes it equivalent, for example, to coffee cup. And then we define two strings. One is going around this hole, and another one which goes from inner boundary to outer boundary. So if one of them is X string and another Z, these two strings do not commute. So I basically define a qubit, and what it really means is that in this case, the ground state should be twofold degenerate. And if we prepare the state adiabatically, we should actually create a state which is superposition of 0 and 1 logical qubit. And indeed, by making the measurements on these strings, we observe that these strings are consistent with at least small coherence present in this logical qubits, and really this constitutes like a first step towards topological qubits. So we're obviously quite excited about these observations. So they allow us to really look to create like and poke and probe this topological state of matter. So it actually is a new tool which is complementary and in a way more powerful than both analytical theories and numerical simulations. In fact, we observe this spin liquid under different conditions from what has been predicted theoretically, and we understand now why. So this type of systems, are very natural for simulating lattice gauge theory. In fact, this state represents emergent gauge theory, something we explore. And more importantly, we really think that, these observations and experiments of this type can allow us to both, gain new insights for engineering topological materials, but also used as a platform for exploiting fault-tolerant quantum information processing. So this actually is a figure from Scientific American, from many years ago, where, probably the artist who drew it, like he or she, thought physicists completely went crazy by thinking about that. But these are the kinds of things we can now really implement in our lab by basically making small holes using laser beams and moving them around. We can really create the, a nuanced and controlled way and break them and explore their properties. So I'd like to shift gears now and talk about another recent advance in our lab, where we use the same platform to explore combinatorial optimization. So this is related to another major effort in the field, of quantum science and quantum computing, to try to solve optimization problems, to try to accelerate the solution of the optimization problem using quantum effects. And the problem which we'll specifically focus on is called maximum independent set. So this problem is a graph problem, can be formulated by by just putting some vertices and connecting them with edges. And the problem is the following. So you'd like to color some of these vertices, but you cannot color two vertices which are connected by the edge. So, and the goal is very simple, is to find how many vertices can we color. So what's shown here is something which probably reminds you, a network diagram which you saw in the back cover of Airline magazine. So this is an example of maximum independent set on a unit disk graph. So basically here vertices are connected only if within given distance, like is shown here. So this problem has many real-world applications, but it's also a very hard problem. It's actually an example of NP-complete problem. But if you followed my talk up to now, you will realize that this problem is very much related to the kind of Rydberg blockade Hamiltonian. Remember, in the Rydberg blockade, we want to excite as many atoms as possible, but we cannot excite atoms within blockade distance. And in fact, it turns out this is exactly the classical part of this blockade Hamiltonian is essentially a cost function of this maximum independent set on the unit disk graph. So what we'd like to do is we'd like to now use our machine to actually solve, to understand if this problem can be solved efficiently. And our approach is to try to go beyond what's called shallow circuit limit to really make sure that correlation spread out across the entire graph. And this is done by using efficient implementation of this graph problem using co-design. So basically the idea is the following. So we'll position the atoms in some disordered array, and each atom will correspond to a vertex of the graph. And then we will adjust blockade such that, certain number of atoms within certain disks are kind of under Rydberg constraint. And then what we'll try to do, subject to this Rydberg constraint, try to maximize the number of excited atoms. So, and if we can do, for example, perfect adiabatic evolution, then this should solve the problem. So this follows a theory idea which we suggested a few years ago. And I should also note that there has been a very nice work by Professor An's group, and I think there will be a talk later today about this. So in particular, in this talk, I will focus on this so-called variational adiabatic algorithm, where we are trying to, find a adiabatic trajectory to solve this problem, subject to this blockade constraint. So in general, it's actually not a simple task. And in fact, to do this, we use the closed loop optimization. We find some trajectory, we define some trajectory, we try to, solve the problem, and then we modify trajectory and try to see if we can improve the solution by trying to find the better, basically, approximation. So there are two figures of merit which we use. One is approximation ratio, which is basically mean of independent set sizes divided by size of maximum independent set. And another one is, so this is, good for trying to find approximate solution. And another figure of merit is a probability to find the mass. So with all of that, we basically implement this approach across hundreds of different graphs. And, we now understand which graphs are hard and which are easy. So I'm not going to go into too many details. But what I'd like to show is kind of our recent work trying to benchmark this solution of using quantum machine against classical algorithm. And here we picked the algorithm known as simulated annealing. So it's basically kind of equivalent, classical equivalent to what we have done quantum mechanically. So simulated annealing essentially tries to cool Hamiltonian to the ground state by stochastically flipping spins, and we try to optimize this algorithm. And then we compare the performance of experiment with this simulated annealing. And what we find, so here are some examples with different graphs. And what we find is that in this two regimes, one is kind of high temperature regime where, basically, both quantum and classical algorithms perform kind of proportionally to each other. But then in a low temperature algorithm, we find that there are some trajectories where basically classical algorithm really gets stuck. And, in some cases, at least, quantum algorithm can solve this problem much better. So what is going on? So how can we understand it? So these turns out that these instances where classical algorithm gets stuck are instances where the problem has a lot of pretty good solutions, but very few actual solutions. And so what these algorithms like simulated annealing do is that they basically try to stochastically at this point flip the spins, and they get stuck in this kind of manifold of many approximately good solutions. And in fact, it determines a fundamental limit to performance of simulated annealing, which you actually can prove, which turns out results in exponential runtime, which scales with the system size. So how does quantum algorithm perform on these instances? So here are two examples. So in some cases, quantum algorithm just solves the problem, and you can see it by either looking at Hamming distance to MIS or to by probability MIS. In some other cases, quantum algorithm also gets stuck. So again, what we do is we generate a lot of instances and just plot the performance of both classical and quantum algorithm at a certain depth, which is shown here. So clearly, what we see here is that in many instances, quantum algorithm performs better, but not in all instances. So what's going on? So basically, what controls the quantum hardness? So it turns out that quantum hardness, not surprisingly, is controlled by minimum energy gap. And actually, if we now plot this minimum energy gap versus probability of MIS, what we find is that this relationship very much follows Landau-Zinner scaling across a wide range of parameters, but not for all. So for some instances, clearly the gap is too small for this given circuit depth to resolve, it. So what we can do then, we can basically kind of quantify. So these are the instances where the system sees the entire graph, and these other instances where it does not. So what we can do, we can basically distinguish these instances, and what we see is that for the instances where the correlations spread across the entire graph, or in other words, where our algorithm is below the speed limit, what we observe is kind of super linear, nearly quadratic speed up in this kind of deep circuit regime. So we are now trying to understand the origin of this speed up and see if we can prove this speed up across all different graphs. We're also exploring if there are some classes of instances where we can see faster than the quadratic speed up. It's connected to something which is called overlap gap property. And of course, we would like to scale up. And that involves a big effort here is to understand and control errors. So I guess I have maybe a few minutes left, and I'd like as an outlook to talk about kind of a new approach which we're now exploring. So far, what I told you is that in our approach, we created an arbitrary kind of artificial crystal of atoms, and then we turn on our coherent evolution and looked at the result. But what if we rearrange the atomic positions during the evolution while keeping coherence? It turns out that this is possible by encoding qubits in the spin states of atoms, in the so-called hyperfine states, where actually they can live for a long time, for a time basically limited by vacuum, by several seconds in our case. And then we only excite atoms in a Rydberg state when we need to execute, for example, a quantum logic operation, a gate, 2-qubit gate operation. So in this case, you can do the following. So you can start with arrays of atoms. For example, here, the pairs of atoms. And what we can do, we can entangle them, and we can verify the entanglement by looking at, for example, parity. But then what we can do, store this superposition in these spin states, and then just move the atoms away from each other and check if the coherence has been preserved. And here we move the atoms across the entire array, and in fact, the coherence is perfectly preserved. So this gives rise to kind of a new idea where basically the architecture of the quantum machine is itself kind of a living organism. It basically changes in the process of the computation. So precisely by using this kind of encoding in hyperfine states, and combining then entangling gates with then kind of rearrangement and proceeding with these operations. So here are some examples. So in the first example, what we'll do is we create a simple state, a cluster state of, in this case, 2 chains. So basically what we'll do is we'll start with atomic pairs, entangle them, then just move one atom of the 2 to the next one, and then entangle them again. And in this case, after reading in different bases, you can measure stabilizers and verify that you have a cluster state. But can we create some more complex state? So of particular interest are the states like this one shown here. It's actually a toric code state on the torus. It kind of seems hard. So this is one of the states which is used for correction, as already indicated. So here we basically will use grid of physical qubits to encode logical qubits, and this logical qubit should be fault tolerant in some sense, and we will use stabilizer measurement to detect local errors. So how can we create a state like this? Well, this state, it turns out to be equivalent to a graph state with non-local connectivity. So where basically, these red atoms are ancilla atoms, and they need to connect qubits, from one, side, basically to another side. So in order to do it, in a lab, we use the old idea of Peter Zoller and Ignacio Chirac. It's actually more than 20 years old, where at the time it was still a time of the magnetic hard drives, and what they started to think about, what if instead of a magnet here, a classical magnet, you have a quantum bit, and you just move this quantum bit around. So this idea was very visionary, but it has not been implemented up to now. So what we do, we implement this idea, but we don't just use one qubit at a time. Instead, we use the entire array. So here is a movie which shows how we can create a toric code on a torus. So each of these ancillas carries quantum information, and this red oval is basically a controlled phase operation. So basically you entangle these qubits across the array, and then you move the ancilla to the readout zone to read them out. So to verify what we actually create a toric code, so we really should check that it encodes 2 logical qubits. And these logical qubits are the qubits, in this case, should be a product of X operators going around this long direction of the torus and short direction of the torus. In fact, indeed, what we find is we find that sorry about that. So let me see if I can do it again. So we find with indeed there are 2 there are 2 non-zero expectation values corresponding to this product of the X operators. And moreover, we have access to all stabilizers. If we basically include these results, what we see is that one of these qubits basically error corrects to 1. It's actually better protected. Another one is error corrects, but not completely, but also to some high number. So this is clearly a very exciting development because it really opens the door for new opportunities to actually build fault-tolerant process, but also it might allow us to combine analog and digital quantum dynamics. And in fact, we already made some steps toward this. So I think I used up my time. So I hope I convinced you that this is really an exciting frontier. And I would like to thank you for your attention and all of the people whose blood and sweat resulted in this work. Thank you very much.
Thank you. Thank you for the very inspiring talk. We are open for the questions. I will start with questions on the chat board. Actually, it's my first time to see any questions on this message tab. Let me translate it for you. The first question is the asker heard that you are going to launch this quantum QERA machine on AWS cloud. I wonder if what kind of programs user can run on this cloud, or how many number of qubits can one program, etc. And what kind of calculations can users do using these machines?
So this will be a machine which will be a programmable quantum simulator, similar to the one which I showed. And it will be around, 200, plus qubits. And basically, what you will be able to program is all sorts of pulses to control the atoms, excitement in Rydberg state. So basically, and also position atoms in a kind of arbitrary ways. So kind of things which I've showed similar to these things, you should be able to do.
I see. And the second question is related to the first one. You mentioned in the last part about the new experiments about quantum error correction using toric code. Is this machine that is available on AWS cloud can do these kinds of error correction now?
That you have to wait a little bit.
I see. Okay, thank you. And yes, please, I'll move on to the questions in the audience.
Hello, thank you for the nice talk. I have two questions about your experiment. One is so I think the addressing of the 2-ether beam is kind of like very crucial for scaling up your system. So could you mention something about your vision about the AOD approach and the SLM approach about it? And let me continue with the second question. The second question is I was a little bit impressed about your coherence of that the superposition state of hyperflying qubit is preserved during the transporting the qubit. So does the qubit gain any additional phase during the transport?
Yeah, so they are both excellent questions. So let me answer the second question. So indeed, it turns out that we can preserve coherence while moving the atoms, which is quite non-trivial. I should note there that this atom movement is accompanied by sequences of pulses which do dynamical decoupling. And in order to do that, we build a very special Raman system, which can basically execute Raman pulses very quickly and very efficiently. And that's a key ingredient which enabled this realization. So the second question is about addressing atoms. Indeed, most of the things which I showed you involved kind of global addressing, and we are actively working on implementing local addressing systems in our lab. So we already we like to think about the systems not in terms of number of atoms which we can individually address, but in terms of number of channels. The reason is we can address with one channel, we can address many atoms. And we are implementing this already in the next generation upgrade in our lab. So it will have tens of independent channels. And we hope very quickly to scale it to hundreds and then eventually to thousands.
So you mean there will be like the hundreds of the atoms per each channels of the laser set?
No, what I mean that we can have hundreds of channels, but each channel has in principle hundreds of atoms.
I see. Thank you.
Yes, we have another question on the online. If I'm correctly translating this, the person asks how to protect the coherence or of the many qubits in your systems by actively or passively.
Yes, so the answer is in practice one would have to do both. So far we only have done it in a kind of large-scale experiments. We have done it passively by using things like, for example, dynamical decoupling. But as I showed in a later part of my talk, in the concluding part of my talk, we're now also making first steps towards active protection. And we basically have all ingredients towards this active protection. So the only ingredient which we have not yet demonstrated, and is something which we are working on, is the so-called mid-circuit readout, that we want to actually read out and see us not at the end of the circuit, but during the circuit itself, and that should enable us to do active error correction.
I see. Thank you. And we can have more questions. Yeah, please.
Thank you for your talking. I want to know more details about the effects that comes from distance between the atom. Is there any ideal distance between atoms?
So I'm not completely maybe understand it. So of course, from distance between atoms, if you excite the atoms in work states, of course, distance plays a critical role, right? If the atoms are under blockade radius and they interact, if the atoms are very far away, they do not interact, right? And this is precisely the effect that we use in many of these experiments, that this distance is what critically controls whether the atoms talk to each other or not.
Thank you.
Did I answer the question?
Yes, we can have more questions if you have any. Yes.
Just probably a basic question. I would really like to understand when the detunings are positive, there was like full circles, and then like it evolves like a Z2 and Z3, and it's like the order changes, and I would like to understand it. Would you help us?
Yeah, so maybe if you can project the slides again, I could just go back to that. So here is, for example, so the idea is, that's one example. Do you see my slide?
Yeah.
Maybe we can even go back to this very basics. So basically here, what we do is we use this detuning as a kind of chemical potential which we can control with external laser field. And basically by making detuning positive, what we do is we favor to have as many Rydberg atoms as possible. However, you have blockade constraint, which does not allow you to have, more than one atom with blockade distance, blockade radius. And so, for example, here, what I will show next is experimental results, where what is shown here is the circle corresponds to basically atom being in Rydberg state. And this image here, the dot corresponds to atom being in a ground state. The reason why it's the case is that at this point, we're imaging atoms which are in a ground state. So the missing atom is a circle which corresponds to atom being in the Rydberg state, right? So here you have a state up, down, up, down, up, down. So here you have a state up, down, down, up, down, down, up, etc. So that's how we can basically, that's how we projectively read out the atomic state at the end. And how we can, see what order emerges. And of course, this is a simple example here. What I showed you also, you can look at much more complex.
So how do we adiabatically change from like one state to the other?
So what we do is we change laser detune, right? So, and here, actually what you see here is literally the picture of quantum phase transition.
Okay.
Right? You see a picture of quantum phase, transition where you change the tuning and you stop at some point. And for example, if you show this, my screen again, you will see that, so here in the middle, in this region, the system cannot decide in which state it wants to be. Either all atoms in the ground state or this ordered pattern. And this is precisely this place where quantum phase transition occurs.